edge designations, CFA Level 1, pre-reading, quantitative methods, Learning Module 6, this is the final module for the Quants methods pre-reads, and basics of hypothesis testing. I'm not really sure why they call it basics of hypothesis testing when they go quite into detail in hypothesis testing, but be that as it may, let's get ourselves going straight away. As per usual, we've got the learning outcomes on the front page for Learning Module 6, hypothesis testing. And as I said, it is quite a long one, as you can see there by all the learning outcomes. Okay. Let us get ourselves going straight away over the page, and we start off with Learning Module 6, Basics of Hypothesis Testing. Okay, and we start off, and just something to remember, we at Edge Designations, we teach across 3 different, and now 4 different designations, CFA, FRM, Kaya, and FDP, and each and every one of those designations has got something to do with hypothesis testing, and each one teaches it in a slightly different manner. So, for example, we're going to go through over here, and the reason I mention that is we say define a hypothesis and describe the steps in hypothesis testing. Now, depending on where you go, some say 3 steps, 4 steps, 6 steps, and even 7 steps. And the truth be told, they're all exactly the same and all get you to exactly the same result. So it doesn't matter. So please don't stress if you've seen somewhere else or in other material that there's 6 steps and here we're showing you 7. I go for the most amount, which is the 7 steps that I've actually seen, to try and make it as instructive as possible. But just before we get going, I know I'm driving people a little bit crazy because we've been doing this for the Learning Module 4, 5. We continue on with Learning Module 6. The same concept keeps coming out. Hopefully everybody's now familiar with it. And remember, guys, that why on earth do we have this whole thing called hypothesis testing? Why do I even need to make a hypothesis? And remember again, guys, why I'm working with a sample. Sample equals the little n. Sample equals sample statistics. Okay. And because I'm working with a sample as opposed to working with a whole population, therefore I don't have all the information available to me. I'm only working with a subset of it called a sample, and based on that I've got to say, well, based on the sample, based on what we're going to see later on at the level of confidence that I use, I can now say that I'm 95, 90%, whatever it happens to be, confident that this is the final outcome after I have gone through the steps in the hypothesis testing. But it's always important to remember that it's just a hypothesis. We presuppose something, I select myself a sample, and I test my hypotheses based upon not the whole population, but again, based upon a sample. And I'm not going to go through this whole introduction for you here. Okay, we have discussed that in great detail. Here's a formal definition if you ever wanted one. Hypothesis is a statement, okay, about the value of a population parameter. So I'm saying something about what, guys? The whole population. But remember, I don't have the whole population in front of me. I'm working with a sample, which needs to be then tested to confirm or deny its validity based upon using a sample. Because remember, guys, again, if I had the whole population, I wouldn't need to make any statements or any kind of test or anything, because I would have the whole population. Okay, we start off over here, and I'm just going to mention this. A lot of it will seem a little bit foreign as we go through it now, but I'm going to go through it in great detail when we do it with you via a nice long detailed example, and we'll take you through in the example step by step by step. Okay, but as mentioned, I like to do a 7-step approach to hypotheses. Some people do 4. I think FRM does 3. New CFA does even less than the 7 now. I'm going to stick to this as part of our pre-read. Step 1, state the hypothesis. In other words, what am I actually testing? Step 2, identify the test statistic, and this should make sense to you now, guys, after we've done Learning Module 4. What is the probability distribution? Is it a normal distribution? Is it a chi-squared distribution? we need to be able to identify that, because when we start to do our test, I can only test and use the correct table based upon what type of distribution I'm dealing with. Step 3, specify the significance level. And remember what we spoke about previously, just by way of example over here. Okay, if my confidence level is 90%, then my level of significance is always the other side of it, which will be 10%. Okay, state the decision rule. Step 4. Okay, that's specify which value of my test statistics must equal, okay, in order to be able to make a specific conclusion. And again, that'll make more sense when we do an example. Step 5, collect the data in the sample. Okay. Step 6, make a decision regarding the hypotheses based upon what we saw in step 5. And step 7, and it's often people make 6 steps, because 6 and 7 do tend to work a little bit hand in hand. Make a decision based on the test result. In other words, take what we got from step 6, okay, and literally make a conclusion. Write it out and say, well, okay, how does it solve or not solve our particular hypotheses or a problem that we're dealing with. Okay, those are the steps, and guys, please don't stress about them just yet. Okay, we will do a nice detailed example of those as we go forward. Okay, the very beginning, okay, is we talk about the null hypotheses and the alternative hypotheses. Okay, and it's a bit strange. Okay, people always ask the same questions when they start to study statistics. You've got the null and the hypotheses. The null has got a symbol called HO. The alternative has got the symbol HA. Okay, and it's an interesting thing, but what we're trying to do over here, we are trying to reject the null, because if I can reject the null, then what can I do? I can accept the alternative. So it does appear somewhat counterintuitive. You're trying to reject something so that you can accept something else. Why don't you just accept it in the first place? Okay, that's not for tonight's discussion. Okay, everybody comfortable with that? And this is one of the early steps in the hypothesis process. We've got to be able to define the hypotheses, both the null, which I'm looking to reject, as well as the alternative, which I'm looking to accept. Remember, if we reject the null, we reject the null in favor of accepting the alternative hypotheses. Okay. And there we go. I've written them out for you there. I'm not going to spend more time here. Okay. Let us move along over here, and I'm going to do an example or two of these, okay, just to make sure we've got the concept nice and clear. Remember as well, guys, when I spoke about in learning module 5, we spoke about undersampling and estimation. We spoke a little bit about one-tailed tests, two-tailed tests, and I mentioned over there that we're going to come back to that when we get to learning module 6, which is hypothesis testing. Okay, here it comes. Watch for it, and let's make sure we are able to fully take it in. Okay. A manufacturer of a new margarine claims that his product is fat-free. However, some of our friends have sampled the product repeatedly and have put on weight. Based on that, we have reason to doubt the claim. And what are we going to do, guys? This is my hypothesis is that what? That the margarine is not fat-free. Does everybody come with that? That's what I'm trying to prove. And why am I trying to prove that, guys? Because he says it is fat-free, the manufacturer, but all of my friends are putting on weight, so it seems to be quite clear that it is not. Okay, guys, I do apologize for the example. It's a bit of an old one. I'm not sure. It wasn't written by me exactly. Came from a textbook, so it is a bit odd. So there we go. Okay, but is everybody comfortable that my job over here, and remember, because we're in hypothesis testing, my job in the hypothesis is to prove that it is not fat-free. Okay. Now let's have a look over here. Okay. Based on that, okay, the HO, which is the null hypothesis, okay, is what I'm trying to disprove. And what I'm trying to disprove, the HO, that the mean, and what am I defining with my mu? My mu is the mean or the average fat content, is equal to 0. That's what I'm trying to disprove. I'm trying to say, no, 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 you are wrong. I'm trying to disprove that in favor of the alternative hypothesis that the mean fat content is in fact what, guys? Greater than 0. Can everybody see that? So look what I'm trying to do. Now can everybody see it nice and clearly? The null hypothesis, okay, is what I'm trying to disprove. I'm trying to reject the null. In other words, I'm trying to reject the notion that the mean fat content is in fact equal to 0 in favor of the fact that the mu, or the mean fat content of the population, is in fact greater than 0. That's what I think it is, because I see my friends putting on weight. Okay, now if I had to say to you guys, okay, what kind of a test is this? Well, there is my normal distribution, there is my mean in the middle. What am I trying to prove? I'm trying to prove what? That the mean fat content is greater than 0. So I'm only, can everyone see why it's very important, guys? This is a one-tailed test. I'm only trying to prove that what? That the mean fat content is greater than 0. So there's my mean and 0. I'm trying to prove greater than 0. So it's a one-tailed test. And of course, guys, it sits in the right-hand tail. Everybody comfortable with that? Okay, let's look at the next one. As I said, guys, the examples are a little bit odd, but I didn't design them myself. Okay. A soft drink manufacturer claims that the tins of his drink have a capacity of 340 mils. Okay. And he says that they are filled to the brim. Some of our friends that purchased the tins have found that most tins are not filled to capacity. Okay. And therefore, we've got reason to doubt the claim, and we want to carry out a test to see whether or not the claim is true or not. Okay, so remember, what are we saying? We're saying that there we go, there's these cans of cold drink, okay, are not equal to 340 mils, and he says yes, they are. I'm saying it's less than 350 mils, and often what helps, guys, if you're battling to set up the hypotheses, often start with the HA. It often helps you. Okay, let's do that now. HA, remember, is the alternative hypothesis, which I'm trying to accept, and I'm trying to accept the fact that the mean contents, the average contents of the drink are what? I'm saying is less than 340. HO, which is the null, is that the mean amount of drink in each one. And what does he say, guys? He says it is equal to 340 mils. And what am I saying? I'm going to try and do what, guys? I'm going to try and reject the null that the drink has got 340 mils in it, and to enable to accept the fact that it's got less than 340 mils in it. Is everybody comfortable with that? Does that make sense? Okay. Again, let's ask ourselves the question, what am I trying to prove? There's my normal distribution. I'm trying to prove that the mean content is, and now remember, here's my mean, here's my, in fact, I want to just draw it over, well, let's put it over there. 340 mils is my middle. That is my what, guys? That's my mean. And I'm trying to say that the contents of the drink is less than 340. So I'm going to be working in the left tail, less than 340. Okay, but again, I'm only working in one tail. Does that make sense, guys? I'm only working in one tail. Which tail is it? It's the left tail. So again, both of my first two tests over here were both one-tail tests. One was the very first one of the fat case was in the right tail. The second example over here of the cold drinks is in the left tail. Everyone comfortable? And let's just do the last one now that we are here. The vice chancellor at a university claims that the pass rate at first year level at his institution is 65%. We've got some reason to doubt his claim, but look at this. Okay, we're not sure whether our doubt stems from the fact that we feel the pass rate is more than 65 or less than 65. I just don't trust this guy. So when he tells me that the pass rate is 65, I think that's a lie. But I'm not sure why he's lying. Okay, is it more or is it less? Look at the test that we perform over here, guys. Okay, so again, H, I'm going to start with HA just to make it a little bit easier. This is what I'm trying to accept. This is called the alternative hypothesis. I'm trying to accept the fact that what? That the mean or the average mark in his institution is what? Not equal to 65. And I'm trying to reject the notion called HO, which is your null, that the mean mark in the institution is equal to 65. Okay, now when I go and draw us a normal distribution, there is my mean of 65. And what am I saying? Well, I don't know what I'm saying actually. What I'm saying is that it's not going to be 65, but I don't really know why I'm saying it. I just don't tend to trust this guy. It could be less than 65 or it could be more. So can you see, guys, over here? Because all I've said over here, guys, is what? That HA, the alternative is that it's not equal to 65, but I don't know what it is equal to, but it's just not 65. Now, so it could be more than 65 or less than 65. In other words, how many tails are over here? 2 tails, both in the right-hand side and the left-hand side. Can everybody see now how we deal with a case then of a 2-tailed test? Everybody comfortable? Okay. There we go. I'm not going to spend too much more time over there. And now if you have a look over here, guys, page 6, I'm not spending any time over here. Hopefully you guys are familiar with this. Compare and contrast one-tailed and two-tailed tests of hypotheses. Is everybody comfortable with that already? Just depends on how many tails we're dealing with and depending on what we are trying to prove. Okay, and I think we've done that in enough detail. Okay. We come to page 7 over here. Okay, page 7 says explain a test statistic, type 1 and type 2 errors, levels of significance, and the power of a test. Okay, and what's interesting that this test of this thing called the test statistic, okay, a test statistic, and I'm going to give you its formal value. Okay, the formal value of a test statistic is it's a standardized value that we have to calculate. The researcher needs to calculate from the statistics collected from the sample. Okay, and the whole of hypothesis testing, it's this easy, guys. Okay, everyone tends to make a big deal of it, but it's really, guys, it's this easy. It's really a case of just comparing my critical value versus my test statistic. That's it. Okay, we'll do it by example for you. Where do I get the critical value from? Well, remember what we said a little bit earlier. We need to determine what type of distribution is this. Is this a normal distribution? Remember, if it's a normal distribution that I'm dealing with, and the question will guide you on that, don't worry, I'll show you that as well. If it's a normal distribution, where do I get my critical value from? By now you're getting bored, I know. The Z table. Okay, we pick it up straight off the Z table. Where do I get my test statistic from? You got to work that out. Let me show you the calc. Here we go. Test statistic, okay, is equal to the sample statistic. In other words, when you ran your sample, what did you get? Less the population value when you are using the null hypothesis. I'm going to show you that as well. Divided by the standard error. Okay, and we'll do a calc of that. But remember, guys, the whole of hypothesis testing is really that simple. It's really a comparison of the critical value to the test statistic. The critical value we get from the tables, dependent on the distribution. So you might need to go to a Z table, you might need to go to a T table, you might even need to go to a chi-square table. Okay, and then we compare that to the test statistic. This formula for the test statistic, guys, okay, is one for a normal distribution. It will change. This calculation for the test statistic will change dependent upon what you are testing. But we're going to show you that as we go through the notes. Okay, let's turn a page. Okay, so just remember again, guys, how do I calculate my my test statistic? Okay, here we go. We'll do this example with you. Okay. And remember this before, from our example about the manufacturer. A manufacturer of a new margarine claimed his product is fat-free. Our friends tested it. We have reason to doubt his claims. What is the hypothesis? I'm not doing this one with you guys. Okay, HO, and that's what I'm, remember again guys, HO, that's what I'm trying to disprove. I'm trying to disprove the fact that what? That the mean fat content is in fact equal to 0 because we think it's not. And remember guys, I'm trying to reject that in favor of the alternative that the mean fat content is greater than 0. That's what I wish to accept. Okay, so what I do, guys, remember, that's my hypothesis. If I had tons of money, tons of resources, what would I do? I would go and find every single tub of margarine out there in the whole world that's ever been sold by this manufacturer and test it. But I can't do that. It's too many, it's too costly, it's too time consuming, etc. What do? I pick myself a sample. I draw myself a sample size of 36, okay, and my variance is 64. Everybody comfortable with that? Now remember guys, the minute you see variance, there's always a little bit of a trick that they like to use. I never use variance, we always use standard deviation. How do you go from, if the variance is 64, how do you get standard deviation? Well, standard deviation is equal to then the root of 64, I think it's 8. Okay, everybody comfortable? So just do that conversion quite quickly, quite early, so you don't get bogged down by that at all. Okay, so I draw a sample size of 36. That will be my little n. And you know what I find? I find that the mean amount of fat is 1.5 kilos. So in fact, you know what? I was probably right. That the mean content is not 0, but it is greater than 0, and I found it to equal 1.5. Remember, my job is not yet done because I still need to work within the hypotheses steps, step 1 through till 7. Or whatever, however many you're using, and follow the normal steps and procedures to be able to come out with a conclusion in step number 7. We'll show you that as well. But for now, what I want to show you is the test statistic. So the test statistic says you take your sample statistic. In other words, when I ran my sample, I'm trying to clean up here. When I ran my sample, okay, what did I get? And I'm going to use colors over here. In my sample, I got 1.5 kilos. There we go, everyone comfortable. Now remember what we said? We said it's always the test statistic, your numerator is your 1.5, which is what you got in terms of your sample, less what the value of the population. Remember, the population value is called the mu under HO. What's it under HO? 0. He said it was 0, didn't he? So my numerator, guys, is going to be 1.5, which is what I said, less 0 over what we call the standard error of the sample statistic. So this, and how do I calculate that? Is always going to be my standard deviation, which we know now is 8, everyone comfortable, divided by the root of the sample size of 36. There we go. Okay, so my my standard error over there is equal to what? Is equal to 8, which is my standard deviation, over the root then of 36. I run all my numbers and I come out with a test statistic of 1.125. And remember, my job in hypothesis testing is then going to be to compare the test statistic to the critical value, and we haven't yet shown you how to get to that one. Everybody comfortable? Okay. Level of significance we spoke about in learning module number 5. The level of significance is really just looking at the other side of the confidence level. Okay. And we'll look at that as we go forward as well. I'm not going to spend too much more time on that. But the level of significance, okay, is often labeled, almost looks a little bit like an alpha sign. Okay, and we talk about the level of significance. Remember, in a test, we've always got to determine, is it a one-sided or a two-sided test? Okay, if the test is one-sided, then what? Then the rejection region. And remember, what am I trying to do, guys? I am trying to reject the null. But the rejected region can only lie where? In one side. Either if it is a one-tailed test, it will either lie over there on the right-hand side or there on the left-hand side. Okay, is everybody comfortable with that? And that's when we talk about the level of significance. Okay, for example, let's just say it's a one-sided test, guys. and I'm talking about a confidence level, let's say 95%. Therefore, my level of significance will be 5%. And if I'm only dealing with one tail, that little bit over there will be the 5% level of significance. Okay, we talk about our rejection region. We'll talk about that when we get to our example. Okay, here we go. Obviously, guys, again, same story. What if I'm dealing with a confidence level of 95%? Then what do we know? Then we know that my level of significance is equal to 5% because it always sums to 100. But what I know, it's a two-sided test. If it's a two-tailed test, then each tail takes 2.5% in each tail. Everybody comfortable with that? Okay, so just always watch out, and then remember, if it's 2.5, then when I'm going to look on my Z table, I'm not looking for 95, am I? We showed you this in learning module number 5. Then yes, you're going to be looking for 97.5. Okay, we will show you that in our example. Okay, and there we go. I'm not going to spend too, guys, there's a lot of extra verbiage or wording over here. I'm going to just try and make it look as simple as possible, which it really, for the most part, is. We've got two types of errors in hypothesis testing, type 1 and type 2 errors. And I want to just pop across here to the table. The table says everything. Okay. Now, if the HO is true, okay, it's true, okay, and what would HO, let's just go back, and I just want to try and make it as easy as possible, okay, let's just say that my HO is true, that, remember what the manufacturer said, he said that the fat content is equal to 0, remember that, remember my example, he said that the fat content is equal to 0, and you know what, guys, it's true. If it's true, what's the correct decision? Well, the correct decision then as a researcher for me would be, I'm not able to reject HO, because remember, what's my job always? It's just try and get this right. If you get this table, you've got it all, guys. HO is equal to the null, and what's my job? My job is to reject it, but I can only reject it if what, guys? If it's not true. But what if it is true? And in fact, the manufacturer was telling me the truth, and the fat content is in fact equal to 0. Then what must I do? What's the correct decision? What's the correct process? Yeah, I've got to fail to reject HO, and that's the correct decision. What if I make a mistake and in fact I do reject HO? I shouldn't have. Because remember, if I reject HO, what am I doing? If I reject HO, then I will be accepting the alternative, and my alternative said that there is fat. But that's not right, is it? That's called a type 1 error. Everyone happy with it? That's where we get a type 1 error, is when I should fail to reject HO, but I don't. In fact, I reject it. I shouldn't reject it, but I do reject it. Why should I not reject it? Well, it's actually true. It's actually true. I made the error. Okay. On the other side, guys, when HO is false, and now let's switch it around. Why is HO false? HO is false because, okay, the fat content is greater than 0. No, sorry, Mr. Fat Manufacturer, you were wrong. We tested the fat content. There is fat in there. Sorry. Everybody comfortable with that? So HO is false, and if HO is false, what's the correct decision, guys? Then the correct decision is to reject it. Yep. There is fat, I reject. What if I fail to reject? I make a mistake and I fail to reject it. That's what we call a type 2 error. Okay. Is everybody comfortable? So guys, remember, your job as a researcher is always to reject the null. That's what you're trying to do, but you've got to make the correct decision when you do it. If you happen to be wrong, and then I've shown you over here, guys, type 1 and type 2 errors. If you get this table, you've got what you need over here. Okay, we move down over here, and just if you wanted a bit of a formal look, type 1 error is I reject the null when it's true. In other words, I shouldn't reject it. Type 2 error is I don't reject the null, and I should have because it's in fact false. Okay, we talk a little bit about the power of a test. Okay, and power generally is concerned with the bottom right block, the probability of rejecting HO, that's over there. Okay, take you back, when it is in fact false. Okay, and I wouldn't spend too much more time over there. Okay, I think the key I want everyone to come out with that you're able to define a type 1 and a type 2 error and know where they fit in on the picture. Okay, but here's a formal definition if you so wished for one. Okay, power is the probability of correctly rejecting the null. In other words, you should reject the null and you do reject the null. Okay, it's 1 minus b. If you got that wrong, that would be a type 2 error. Okay. We now come to the next part of the hypothesis, which is called explain a decision rule. What's a decision rule? Okay. Well, when I start with my decision rule, okay, I'm starting with things called levels of significance, things like that. Okay. And remember, we've spoken consistently, okay, about the relationship between confidence levels, intervals, and tests of significance. We're not going to spend too much more time over here, over our page. Let me show you that. Okay. And I'm going to show you that much more so than by way of example. And we just mentioned an interesting concept over here, a statistical result and an economically meaningful result. Okay. A statistical result is when I run all my statistics, okay, and I come out with a result. Okay. And it's a hypothesis test. I do all my samples, I do everything like that. An economically meaningful decision takes into account the relevance of the statistical decision, but it also considers factors that are non-statistical. Okay, things like, well, what would this cost me? What are the transaction costs involved? Are there taxes? What's the risk involved? All other things that are not statistical in nature, but again may have an impact then on my test. Okay. We also have this concept over here called p-values. There are 2 ways to do a hypothesis test. Way number 1 is to do the normal way, which we've shown you step by step for the 7 steps. And again, I'm going to show you an example now. And then we've got another way of doing it, which is called, it will give you a carbon copy result, guys. And that's called using the p-values. Again, I want to do that by way of example. But here are your steps. You can see the steps are quite similar. Step 1, state the hypotheses. This is when I'm using the p-value, guys. Step 2, identify the test statistic. Don't forget to be able to identify what kind of a distribution we're dealing with. Specify your level of significance. Okay. State your decision rule. And this is all when I've got what, guys? This is my normal approach. We're just going to contrast the normal approach with the p-value approach. In other words, the 7-step approach versus what you can leave out in the p-value. Step 6, make a decision. Step 7, okay, conclude on your decision. When I'm using p-value, let's just change our color. When I use p-value, step 1 stays the same. State the hypothesis. Step 2 is the same. Identify the test statistic and its probability distribution. Step 3, collect the sample data. Step 4, calculate the p-value. Step 5, make a decision, and step 6, conclude. So you can see we do drop one of the steps. What exactly is this thing then called the p-value? The p-value is really just working with hypothesis testing the other way around. Okay, it's the area from my test statistic to the end of the tail. Generally speaking, okay, I'm just going to give you just a general way of looking at p-values. If I'm working with a 5% level of significance, okay, what do I always want for my p-values? I want values that are lower than 5%, because then what can I do? I can reject the HO. Okay, so just remember p-values, that's the tail, and what I'm typically trying to do is I'm trying to reject that amount, reject the tail, okay, because then I'm going to be rejecting the HO, the null, which is exactly what I'm trying to do. Okay, so yeah, look over here, guys. I'll just give you some little examples. Okay, My level of significance is 5%, and I'm given the following p-values. What are my correct answers? Number one is 2%, so I will reject HO. Why? Because it's less than 5%. 4.5%, sorry, 45.6%. Fail to or do not reject. 5.3, because both number 2, okay, and number 3, what are those, guys? Both of those are greater than 5%. You can see that. Therefore, my answer is fail to reject or not able to reject HO. And the last one is 0.00001, which is very low. Fantastic. I'm able to reject the HO. And there are your various steps involved. Okay. Good. And that takes us then on to page 16. And we have our learning objective over here. Describe how to interpret the significance of a test when I'm doing multiple tests. Okay, a type 1 error. What is a type 1 error? Is the risk that I reject, okay, a true null hypothesis. Because remember, if the null hypothesis is true, what should I do? I should fail to reject. I shouldn't reject it. Okay, we often call that that's called a false. It's called a false positive. Okay, often denoted by the FDR, the false discovery rate, okay, and that's often called the multiple testing problem, okay. The false discovery approach to testing is an approach that requires adjusting the P when we run a series of tests, okay. And you can see over here, guys, what we have is, okay, the test statistic again. I'm not going to spend too much more time over there, okay, and what we're going to come out with by the time we are finished over here is we need to determine when we get to the various, okay, test statistics, okay, which ones are used depending on which type of distribution I have. Remember, we've got T, Zs. We'll talk about those as we go. Okay. Something we haven't spoken about much in the earlier learning modules, because it's covered more in the core materials, is that when we get to a certain size, which we call very large sample sizes, okay, the central limit theorem, we didn't speak about it much because it's more in the core syllabus. Then what we do is we treat T distributions like Zs, because they become so big they start to approximate a Z. If you've got that, great. If not, we will see it again when we get to our cases, when we get to the core syllabus. You've seen all of this before, guys. There's a bit of fair measure repetition. There is my, okay, my test statistic. I'm not going to spend too much more time there. Okay, and let us move on a little bit over here. We do talk about this a little bit over here, guys, the Z test. And it's a bit of a challenge. They do keep it in here, but it wasn't covered that much then in the earlier learning modules. As I said, it's covered in the core. And what we say over here, guys, I'm just going to summarize it very briefly for you, but we do do it in the core syllabus, is that when we have a central limit theorem says when we've got a very large sample size, most people say a sample size of at least 30, then what happens? Even if it is we should be using what we call a T distribution, okay. The larger the sample size, says the central limit theorem, okay, the larger the sample size, it starts to approximate a normal distribution. If it's a normal distribution, well, then I can go and use my Z table. Okay. What we're going to do over here, guys, as promised about time, I'm sure you're all thinking that, okay, is our example that I promised from the beginning. Let's go and do a nice example together with you. Okay, and we're going to do step by step, and I'm going to do both approaches, the normal approach, which is the 7-step approach, as well as the null, the p-value approach. Okay, let's get ourselves going straight away. The information department of a college put out a circular indicating that the average grade of their students was 70%. The standard deviation related to those marks was 10%. Comes out a statistician and he says there's no way. And what does he say? He believes that the average grade quoted of 70% is way too high. He says, no, listen, hold on a second. I've met your students, and unfortunately, As much as you like your students, I like them too, but they are not 70% students. I'm sorry to tell you, so says the statistician. And he wants to test if this is correct. So what does he do? He runs himself a test. He draws a sample of 36 students, okay, and he finds the average grade is 67, and he's using a 95% level of confidence level, which is a 5% level of significance. Now, remember, what's important to remember, okay, is the fact that, yes, his sample generated an answer of 67%. So what would you say? Well, he's proven his point, because what was his point? His point was that the information department said that the students are 70% students. We did a sample and the sample says 67. Why can't we stop over there? Of course we can't stop over there. Reason being, guys, is because we need to finish the entire, because really I'm working with what? A sample, not the whole population. I've got to finish the entire, what we call, okay, hypothesis testing procedure, guys. Is everybody comfortable? So let's go. Number one, state the hypotheses. And remember, guys, my theory is that the HA, the alternative is that the U, or the mean, it looks a bit like a U, but it's the mean, that the mean marks at this particular, okay, college are less than 70. Again, if I just draw that for you on a normal distribution, there is your mean. Your mean marks would be 70, and I'm saying they are less than 70. So one-tailed test, guys. And which tail? It's the left-hand side. Everybody comfortable? Okay. But what is he saying? What is the information part saying? They're saying no. The mu, the mean, the average mark over here is equal to 70. And remember, guys, what is my job as a researcher? My job is to reject the null in favor of accepting the alternative that the marks are less than 70. Step number one, we have done. Step two, what kind of a distribution? Remember, guys, makes no difference over here, because remember what we said a little bit earlier, at the minute you've got a suitable sample size, okay, that's above 30, what would we say? Okay, that doesn't make a difference, we can use a Z test anyway. Okay, a normal distribution, we can use a Z test. Step 3, specify my level of significance given to us in the question, 5%. State my decision rule, step number 4. Guys, remember, where are we? We are in the left tail. It's a one-tail test. We're in the left tail. What do we know about if we've got a level of significance equal to 5% or 0.05? We know that if I look at the Z graph, I would get to a value on my Z graph of 1.645. Let me just show you that quick, just to make sure everyone gets that. You can learn those off by heart, but let me show it to you on the Z table. Let me just hop across it. There we go. I'm going to make this a little bit bigger. There's my Z table. Oops. Okay. Now remember, what am I looking for? It's a one-tail test. I'm looking for a number over there of, okay, 95%, because remember 95 is the level, is the confidence level. So I look over here, I look over here, and 95% will sit somewhere there. Does everybody agree? Remember, why am I looking for 95 when my level of significance is 5? Remember, everything sums to 1. 1 less the 5% level of significance gives me my 95. We work across the graph over here, so it's 1.6 and somewhere over there 4.5. Is everyone happy how I got to that? I don't have exactly 0.95, I work in the middle over there. Let's go back to our numbers over here. But remember, it's not now, it's not 1.645 because I'm working in the left tail, because I've got a less than test, so it's actually minus 1.645. Remember what we said, that minus 1.645 then sits over there in the left tail. That is my region. Everybody comfortable? I've now set everything that I need. Okay, that's my decision rule. Step 5, you know what's coming, is we need to calculate my test statistic. Okay, let's have a look over here. What's my test statistic? We know all the numbers. I'm going to write it out for you over here, that my test statistic is equal to my x bar, in other words, what did I say it is, less what it is in terms of the mu or the population over there, okay, over the standard deviation, okay, over the root of n. Okay, my standard deviation is equal to 10. Let's plug and play some answers over here, guys. Remember, what did I say when I tested the results? I got to 67%. What did the information department say? They said 70%. So guys, can you see straight away I've got an answer of -3 as my numerator. I'm going to get a negative answer, and that makes sense because I'm working in the left tail, aren't I? Okay, standard deviation is 10. The root of my sample size was 36, so putting all my numbers in, that's going to be 10 over 6, and my answer is -1.8. What my answer for what? My answer for the test statistic is -1.8. Remember, guys, what's our whole job? Is I'm going to compare my test statistic versus my critical value. My critical value I've got -1.65. My test statistic I've got -1.8. Is everybody comfortable? Okay. What do we now listen to the conclusion? Okay, where is, there it is. That over there would be -1.645, which is equal to my critical value. Now look at the conclusion. I'll read it to you verbatim. Since the value of the test statistic, it's -1.8, is more extreme than the critical value of what? 1.645. It's more, moves away more to further away from 0. Okay, the test statistic falls in the rejection region. Now rejection, now you say to yourself, have I done my job? Yes, I have, because my job is to reject the null, and I've managed to do that. Why? Because my test statistic is further away from the critical value. Now listen to the phone call that you make. You phone up the information department, and what can you say? Can you tell them that they are liars and that their students did not get 70%? No, you can say, you can conclude that the average marks of the student at the college were less than 70% when testing at a 5% level of significance. But remember, if I tested at any other kind of different level, I couldn't make the same conclusions, could I? So I can only say, listen guys, I know I'm 95% sure that what you're saying is not true, but that's all you can say. And I'm showing you on top of page 21. Okay guys, I do suggest that you take a look at it and work through it. But and what we say over there is, what if we change things around a little bit? We change the sample size. We change we work not at 5%, but we work at 2.5%. Things will change, guys. So just look at that. It's a very interesting, some interesting observations over there. Okay. What we show you over here, guys, is what would happen, okay, if I was working with we carried out what, guys? A one-tail test. But what happens if for some reason or other we were asked to carry out a two-sided test? What would I do? That 5% level of significance would have to do what, guys? Have to be 2.5 in each side. And now it would now my critical value, which was 1.645 before, now and that's for a one-tail test. What would it be for two tails? 1.96. Why? Because for a one tail, I put, just change my color here, you can see it nicely. For a one tail, I put all 5% in one tail. For a two tail test, I put 2.5% in each tail. Can you see how things would differ, guys, depending on what we are given in the particular question? Okay. And again, we do the whole thing again. I'm not going to do that with you guys. I think I'll make you completely mad. We'll do the whole thing for you again over there, under the assumption then that it is a two-tail test, and I'll do everything again there for you, but we're just assuming that it's a two-tail test, all the rest of the steps there. Okay. Sorry. Now we're going to look at the particular example. Remember I said you will do it first normally, and now I'm going to do it with you using the p-value approach. Okay. Now, let's do everything stays the same. We're not changing any of the data, any of the information. We're just doing it on a p-value approach. Step 1, state the hypothesis, same story. The alternative hypothesis is that I'm saying that the students are worth their mean, their average mark is less than 70. Identify the test statistic as well as the probability distribution. It's a Z test. Normal distribution Z test. When I go and did, and I'm not doing this with you now, guys, because we've done it already, haven't we? Do the test statistic, that's still 1.8 negative. Okay, you remember how we got to that, guys? Just to show you that again, just in case you were, remember, what did we say? We said the test statistic was 67. That is what we called X bar, my result, less what it is under normal circumstances of 70. Okay, and then we took the standard deviation of 10 over the root of 36, and I got to an answer of minus 1.8. Everybody comfortable with that? Okay. Step 4 is where the changes come in. Step 4 is calculate a p-value for the test. What is a p-value? A p-value says, well, hold on a second. I've got a number of what? 1.8. Negative. What is that in terms of numbers? Ooh, well, remember again, guys, what am I dealing with? I'm dealing with a Z table. Let's go to the Z table, and let's see if we can find 1.8. Okay, so let us hop across to my Z table. Let's just clean it up over here. Remember, the p-value is 1.8. Let's see if we can find it over here. There is 1.8. Is everybody comfortable? We go down, 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 down there. And there's my number. 96.41. But remember, that is for what, guys? Positive 180. Is everybody comfortable? So what is my p-value? My p-value will then be 1 minus 0.9641. Okay, everyone happy how I calculated my p-value? Because now step number 1 was what? Step number 1 was calculate your t statistic. My t statistic was equal to minus 1.8. I go look on the Z table. Where's 1.8? Well, it's there. There. I go down. I meet my point. And now we're going to go 1 minus 0.9641. And I get to a p-value. P is equal to 0.0359. That should excite us all, because remember, guys, we always wanted a p-value of less than 0.05, so we should be able to reject that. What I want to show you something interesting is that the Z table has also got a negatives table. There we go. Look over here. Okay, here is my Z table, okay, for all the negatives. Okay, so you could also just go for the negative table and we go find ourselves minus 1.8 over there. Everyone comfortable with that? So, and then what I get, there's my actual number of 0.0359. You happy with that? But just in case you weren't given a negatives table, all I do is I take the same number that I got and I'll do 1 minus that, which I've shown you on the very first table there. But end of the day, guys, we've got our p-value of 0.0359. Let's go back to our main page over here. Okay, and from the Z tables, my p-value is 0.0359. What could we conclude? We conclude that that is less than 0.05. I'm very happy because now I can reject the HO. And can you see, guys, well, step 6 will make our conclusion. But what do you notice? We notice that we can reject in both cases. When I use the normal 7-step hypothesis test, or case number 2, when I use p-values, both times I rejected the HO. Okay, so you're going to get exactly the same result. It's just 2 different ways of doing the same test. Okay, there's a few additional points over there related specifically to the p-values that we just did over there. Okay, what we're going to do for the balance of this particular learning module is to say, well, hold on a second. Okay, what if there are there other kind of tests that I need to be working with? Okay, up until this point we dealt with very simple tests. From page 23 onwards till the end, we're going to be dealing with other types of tests which become a little bit more complicated. And the only thing that changes when we move through the various tests is that my critical value will change, because I won't be using in most cases a Z table, and my test statistic will change because I'm going to have to calculate a different test statistic to match the specific table that I'm looking at. But that we will leave then. We've done enough for video number 1. I think that's enough for everybody to take in. We'll do the balance then in video number 2, continue on with page 23.